Okay, so first of all, there are some few things, and everybody, you can stop your stop taking notes, and you can just focus on the screen that I'm sharing. And I had some questions for all of you, and let's see whether we have done that part or not, so that whatever we do going forward, we can fine tune and find out ways to make sure everybody is able to participate correctly. Okay, so first of all, everybody has done GCC, C plus, at least C coding, basic C coding. Everybody has done in our school, in our college times. Just a yes if you have done it. The C programming, little bit of, not to a very high extent. Okay, so generally what happens is whenever we start to build a chip or start to model a chip, the first step that we generally follow. Okay, so by the way, whatever I'm saying right now, these are all valid for one of the chips that was taped out by our company. Maybe I'll just stop share. So whatever you're seeing right now, it is all valid for this chip, and everybody is able to see my screen. So this particular thing that you see, this rectangle thing, it's one of the chips that was taped out by one of our students. So whatever explanation or whatever the way we are going to model the whole thing, I'm going to explain few modeling techniques. Whatever we are explaining now, it's all valid for a chip that was already taped out. So it's a silicon proven. Whenever we talk about this, we are talking about it's a silicon proven thing. Okay, and silicon proven is a very important term in the VLF industry. So as long as you're there in the industry, you will hear the word a lot, silicon proven, and that holds a lot of value. The moment you say that your workshop, your program was silicon proven, that just raises your bar in the industry. Anyways, so the first step what we do is generally we have an application. We can think of an application like PowerPoint, Excel, Word, the Zoom itself, the Mozilla Firefox, and all of it. Those are basically termed as an application. So our task, our end goal is to make sure that that particular application runs on the chip. That's the end goal that we have to achieve at the end of a chip design cycle, which is close to a cycle of 14 to 16 months. Okay. So the first step is we'll just try to understand that in a form of a C code, and then it will be easy for us to go forward. So when we think of an application like a C program, just let's say a calculator C program. So the first step that we do is, if let's say now if you want to design a processor, so all the explanation that I'm going to give to all of you, it's keeping in mind that we are trying to design a processor. So we are just taking a bar upstairs. We are just lifting our bar, and instead of designing any IoTs or some of the other application, we will go to the core of it, which is the processor. And processor is something which is there in every devices. It will be there in laptops, mobile phones, everywhere. The processor is a very common thing. So we'll design the processor itself. It's the heart of the CPU is the heart of the any electronic device. So assuming that there's an application, and let's assume that that particular application is written in C language. The first step that we are going to do is we are going to test whether the application itself is correct or not, correct by construction. And we use GCC. Everybody is aware of GCC. Just type yes in the chat box if you guys are aware of what GCC is. It's a compiler generally. So most of you might be aware of what a GCC is, right? Okay, so GCC is basically compiler. It's a way to compile any C code in Linux. So we use GCC. So we take the application in the C language, we compile it with GCC, and we measure an output O0. That is the first step that we do. Second step, now the processor that we are trying to build, we don't directly jump into writing the RTL code for the processor. We first of all model the entire specifications of the processor in a C kind of environment. For example, in this case, the most of the compiler that we have used, that's basically called as RISC-V GCC, but that's very detailed science. We'll not get into that. But in a nutshell, we'll not design the chip as it is. We'll not start by designing the chip by writing the Verilog code. We are going to first of all model the specifications, and we are going to test whether the specifications are correct or not. To do that, we'll model the specs in a C kind of format. Okay, these are not something that you're going to do in the workshop. This is just a flow, and I'm going to explain exactly where this particular program actually fits. So that's why I'm giving you the background. So the specifications is basically model as a part of using C, and the same application that we just tested using GCC, we are going to test the same application using a specification C model. In this case, it will be RISC-V GCC, for example, just like, or ARM GCC, or it could be x86 GCC. It could be any processor architecture compiler. So we are going to do that and compile it using a RISC-V GCC in our case. And we are going to measure an output O1. Okay. The whole purpose of this exercise is to make sure that your O0 is equal to O1. Once that is done, we can close on one session on one target, which says that your specs is actually freezed. We can freeze on the specifications. That is the very first step that happens whenever you're planning a processor chip to be sent to the market. Is this part clear to all of you? Just type yes if this part is clear. Very simple. We take an application, we run it using GCC. Same application, we run it using the specifications and test whether O0 is equal to O1. All right. Is that okay? All right. Next step. So once that is done, once we are very sure that your specifications are perfectly fine, next what we do is we write a soft copy of the hardware. Okay. So when I say soft copy of the hardware, using RTL, Verilog is a very common language which all of us might be aware of it. But there are some industry languages like BlueSpec or Chisel, or some of the high level languages which is not exactly Verilog, but which is very close to, it's a more abstract level compared to Verilog. So it is not exactly C, but it is not exactly Verilog. It lies somewhere in between. So it becomes easy for us to program the hardware the way we want it to be. So the second step is to basically take this particular specs, understand the specs, and write a hardware or a soft copy of the hardware. This is not real hardware. So by the way, as VLSI engineers, as semiconductor engineers, for us, hardware is basically AND gate, OR gate, flip-flops, and that's basically what hardware eventually means to us. We are going to the physical layer. We are going to the very bottom layer where we are trying to play with AND gates, OR gates, and these kind of gates. When I talk about the soft copy of the hardware, it's basically a representation of the specifications in one of the languages. It is not exactly Verilog, but it eventually boils down to Verilog. But there is some languages, let's say BlueSpec or Chisel or some high-level languages, where you model the specifications in that particular language. The next step is very simple. You take the same application that we started with, you run that particular application on top of the hardware that you just created and measure O2. And the purpose of this particular exercise is to make sure that your O1 is equal to O2. So that way we are actually retaining the functionality. So the functionality is retained on whichever model we go to. And we are going a step-by-step process in designing our real hardware. Okay, so the second step is to make sure that the application runs on the hardware that we have designed using Verilog code, and you measure an output O2. Your O1 should be equal to O2. So is that part clear till now? I mean, how are we going step by step? We are entering into the SOC. Okay, if that is clear, next step is where your actually SOC design actually starts. So we are going to divide the Verilog code into multiple things. So first set, we are going to split the processor outside of it, the actual processor, and we are going to separate out the peripherals and the IPs. And so these are again Verilog codes. The speciality of these Verilog codes are the processor Verilog code will be a synthesizable code. And now what is synthesizable, what is functional, all of it will be very clear as and when we go through the program. But in a nutshell, we write a Verilog code which is synthesizable. It means that we are writing a Verilog code which can be converted to gates easily. Now Verilog is very close to C. It has got some constructs. Let's say it has got a MOS construct. It has got some AND construct. There are some primitives. It's called as Verilog primitives, which are not synthesizable to gates. So we have to make sure that while we write the Verilog code for the processor, it should not have any construct or any primitives which is not synthesizable, because we want to convert them to gates. That's where we have written over here, processor should be synthesizable processor. The Verilog code for the processor should be synthesizable. And these things are something you are going to learn through experiments very soon. Peripherals will be of two types. One is the macros, and macros are some blocks. There are some blocks in the whole design which are basically repeated multiple times. For example, if I want to design a clock divider, for example, and the chip needs, let's say, 10 to 15 clock dividers. So I will not write the clock divider again and again. I will not do a PD for clock divider again and again. I will build it just once. I will do the PD of that particular clock divider just once and instantiate it multiple times. So that's basically called as the macros. This is a very common terminology for the macros. And these are basically a part of the peripherals that part of the peripherals can be divided into macros and analog IPs. Analog IPs are the ones. So, for example, your chip by itself, functions using the logic 0 and logic 1. So they basically uses logic 0 and logic 1s. But naturally, the world has given us analog signals. There is nothing called as a digital signal available naturally. For example, you see the thermal power, you see the thermal stations, you see the hydropower plants, all of it, we use water to generate electricity, and that electricity is analog in nature. There is no mechanism yet to generate a digital signal naturally. To do that, but our processors understands logic 1, logic 0. So we have to find out a way to convert this analog domain to a digital domain. So one of the very popular IPs is ADC. It's a 10-bit ADC. That is what we use as very popular IP to send the signals from the outside world to the processor. Second very common IP is the outside world. Outside world is not able to send high frequency signals to a chip. So your chip peripherals, they generally are able to pass 5 megahertz, 10 megahertz, or maximum 20 megahertz, but your processor might actually operate at 100 megahertz. So internally you would need something called as PLL or clock multiplier. Again, all of this will be very well clear when we go forward in the program, but you would need something called as PLL, phase lock loop, or clock multiplier. We call it as clock multiplier. So those are basically called as analog IPs. Now there is a difference that you see over here. You see over here I have written synth RTL, and over here I have written functional RTL. What does that mean? These macros, the macros that the Verilog code for the macros and the Verilog code for the processor, the criteria for them is that it should be synthesizable to gates, AND gate, OR gate, flip-flops, and things like that. On the other hand, the analog IPs, we to build these IPs, we use something called as NMOS, PMOS, and all the transistors. So we just care about the functional RTL of this particular analog IPs while designing an SoC. What does that mean? So this particular IP, the Verilog code for this particular IP, it need not be synthesizable because we are anyways going to replace it by MOSFETs. That's why this need not be synthesizable, and this has to be synthesizable. This has to be synthesizable. Now all these three terms, synthesizable, not synthesizable, IPs, macros, there is a lab for all three of them. Once you go into your second week, there will be lab for all three of them. So this will be very much, you will be able to visualize this thing once you go forward. But for now, we'll just try to understand that the soft copy of the Verilog code is being divided into two different parts: processor and the peripherals and the IPs. And the processor has to be a synthesizable processor. Peripherals, the macros has to be synthesizable, and IPs it need not be synthesizable. So these are some of the fundamental terms that we are going to understand from a top level point of view, and then we are going to do labs for each and every one of them. Okay, so once we do that, we integrate. There is an engineer. He's an SoC designer or an SoC engineer. He takes up all the blocks, all the respective blocks. He plugs it the way it is supposed to be. It is supposed to be there. He connects the entire SoC with something called as GPIOs. It's called general purpose IOs. SoC is called as system on chip. So there is one engineer who does that, who makes the SoC, who connects it to the GPIOs, and the same application program that we started with, that is again passed through the SoC, and we measure an output O3. Okay, and the purpose of doing all of it is basically to make sure that our O1 is equal to O2 is equal to O3. So we do all of it is because to make sure that your application functionality is not changed, and we are now getting very close to designing a hardware for this particular application. Is that part overall clear? I'm very sure this might be a little bit of a bouncer, but once you start with the labs, I think this will be very well cleared in the labs as well. But at least the top view is clear. At least when we look from the top side, is this part clear to all of you? What are we doing step by step? Okay. Now, a very popular question which is being asked in college interviews is that what is the difference between a microprocessor and a microcontroller? So this by itself, this by itself is basically called as a processor. And once you club the processor with all the analog IPs and all the analog macros and create an SoC out of it, it is basically called as a microcontroller. Now, two very popular examples of this one. Everybody must have done in your college semester 3, semester 4, 8085, 8085 or 8086. Everybody has done this thing, this 8085. Yeah. So 8085, 8086, those are basically microprocessors. You must have seen the kit for running that microprocessor. It is this big. You basically punch in the assembly code and things like that. So it becomes a very big kit because it's just a microprocessor. To make that microprocessor work, you will need all the peripherals to make sure that the microprocessor works. But everybody must have seen the Arduino boards which has got 8051 or Atmega 51. You must have seen that board. Those are very small boards, right? Everybody must have seen the Arduino boards, and you will see one single 40-pin chip which is there at the center of the board. Everybody must have seen that kind of boards. I don't have an Arduino board, else I would have shown that. But everybody must have seen it somewhere in your college or somewhere in your labs. So it is just one board which has got a 40-pin processor inside it. 40-pin controller inside it. That's basically called as a microcontroller. And why it is called as a microcontroller? Because it has got ADC, DAC, all the IPs that is need to make the processor work. That particular 40-pin chip has got everything. That's why it's basically called as a microcontroller. So very popular question when you go for Viva, 8th semester, they ask you what is the difference between a processor and a microcontroller. So this is basically an answer to that. And there is a reason behind why it is called a processor and why it is called a microcontroller. There is a reason to that, and this is what the actual reason is. Okay. Anyways, coming back to the program. Now, once we have done the integration, we have plugged the blocks and we have done all of it. The next step is to actually do the physical design flow, RTL to GDS, where you have all the macros, IPs, processor, everything will be now beautifully placed and routed, and we will make sure that we do the entire physical design using normal steps: floor planning, placement, CTS, routing. In this particular program that all of you are going to do, you are going to focus on one block, which is this blue block, and we are trying to understand all of these concepts using this particular blue block. We're not going to do the entire chip because entire chip the cycle is close to 14 to 16 months of task, but all of you will be focused on this particular block, on the blue block, which is marked over here, and all of you will be working on this particular blue block for the next 3 weeks, and all these concepts will be explained with the help of this particular blue block. There's a small IP also that all of you are going to design. You're going to design a small inverter IP, and you're going to plug that inverter IP over here, and you're going to see how all of this actually function together. When you want to do all these three things, how do you basically do that as a part of a real physical design engineer? So all of this will be covered very soon. But in a nutshell, you will be working on this square block, not on the whole chip. Okay, so once we do this thing, this is a step where your front end, your RTL is basically converted to gates, and these gates are properly placed and routed. So these gates are basically placed and routed. You have all the AND gate, OR gate, flip flops, everything. There is no more if then else statements over here. In this particular step, there is no more if then else and all of it. It is only metal layers. There are only standard cells. And in fact, even if we go one level below, if it want to talk one level below, it has got only transistors. Just a minute. Yeah, so if you want to talk about even more detail, this particular at the output of this one, you will have only transistors, and even if you want to go one level deeper, it has got only metal layers. All these metals and the transistors and the polys, they function in a way that it is going to give you the same functionality. It is going to giving the functionality that we expected to achieve. Okay, so once we do that, the next step is it creates a file called as GDS2, Graphical Data Stream Information Interchange. This is a full form of GDS2. It creates a file. It's a file which has got only metal layers. It has got something metal. It has got information for the fabrication manufacturer to fabricate your chip. This particular GDS, I'm going to show you an example of GDS2 also. So this GDS2 goes through some again set of steps, DRC, LVS checks, and there's a reason for this. This GDS2 is so big, it will be very difficult to run an application on a GDS2. That because these files are too huge. It will need huge compute to do that. So a smarter way to do is DRC always. Now, what is DRC always? Little bit will be covered as a part of an overview of this particular thing. So we are going to cover that as a part of a little bit. We are going to cover it over here. Your GDS2 goes through some checks to make sure that your connectivity is retained. And once you do that, you send this particular file to the factory. So this process of sending the GDS2 to the factory is called as tape out. That's why we always use the word a lot in the industry. It's called tape out. Okay, and it doesn't stop here. Once you send your file to the factory, the factory is going to give you chips back. And that process, they are going to give you this chips back. What I showed you in the beginning. They're going to give you chips just like this. They're going to give you just this square, the chips which is rectangular in shape. And this is what you're going to receive, not the board, only the chips. So you're going to receive the chips, packaged chips, and packaging is again a different world. So you are going to get a chips which is all packaged to the pins. This process of getting the chips back from the foundry, it's called tape in. Okay, so sending is called tape out, receiving is called tape in. So these are very important terms, I think, which all of you will be learning very soon. You're going to use it very frequently in a part of your jobs, in a part of your career. Once we get this particular chips back, our next task is to prepare a board like this, because the chips will not function as it is. You need to give some. There is a memory over here. There is a USB controller over here. There is LDOs, low dropout voltage regulators over here. There are crystals over here that will supply the clock. So you need to give all these peripherals. You have to write the firmware, write the software for it, and just make sure that our application, we are able to send the application through this particular pin, through this particular USB pin onto the chip. We are able to do all of it. And the same application, which is written in the C language, which we were started with, we are going to run the same application on this board and generate an output O4. The entire purpose of this one is to make sure that your O1 is equal to O2 equal to O3 equal to O4. Once this happens, we can successfully say that our chip design is done perfectly fine, because the application that we started with, it's able to run on a chip which has got our own specifications, or your processor basically supports this kind of application. That is what we can safely conclude. The steps starting from this part to this part is close to about 14 months. Worst case it is about 14 months, and the reason for that is 4 months has been taken by the foundry itself. 4 to 6 months has been taken by the foundry, because foundry takes time to get the receive the GDS to do some checks. Foundry has to do some manufacturing and then give the chips back. There's a lot of work involved over there, so it takes about 4 to 6 months to get the chips back. At least for our case, the case that I'm talking about, it took us about 4 months to get the chips back. And once you get the chips back, now this chip is basically readily available for the market. Once we have tested this, we'll identify some markets. For example, iWatch. So iWatch is very high frequency. It needs frequency close to 1.2 gigahertz and in that range. And the processor that we are designing, we are going to you will also get a feeling of how do you basically measure the frequency. So the processor that all of you will be working on, it will operate at 100 megahertz to 130 megahertz. Now, why 100 megahertz? Why not? Why 130 megahertz? And why not 1.2 gigahertz? This is all coming up as and when you go through the entire program. This is all coming up. But currently, the processor that we will be doing the chip design for, it works only for 100 to 130 megahertz. So the best market for this particular chip to go into is, let's say, Arduino boards. So we have these Arduino boards that uses 8051 old processors. Those chips can be easily replaced. In fact, one of the I can show you one of the boards which I have that is very similar to the Arduino board. It's a RISC-V board. So this is one of the boards that was designed by us, and this chip is again a RISC-V chip. So this particular chip is a RISC-V chip, which is operates at 50 megahertz, and this is a very simple a very simple board which can replace Arduino Uno board. Okay, so this is one of it. And if I wanted to show you, this is how the original Arduino board looks like. I'll show you that also. So this is how original Arduino board actually looks like. This is one of the RISC-V chip, and this was an Arduino compatible board that was created by some of our past students. And I wanted to also show you how does the 1.2 gigahertz boards look like. I don't have it right now. Okay, maybe next time when we meet, I'll keep it handy. Yeah. So coming back to so in applications like an Arduino board, we can easily plug in this particular chip, because Arduino needs about 25 to 30 megahertz or 50 megahertz of max frequency which you can use. TV panel. So TV panels has got two sides of it. One is the side where you use the Wi-Fi, the internet side of it, and there's one side which doesn't operate at much high frequency. So these chips can actually go into that area. AC applications. So if you look into all the ACs that you have, they don't need at high frequency, and also they can easily operate 100 megahertz to 130 megahertz. So this is basically the entire flow of whatever all of you are going to